Yeah, my name is Jan Peters. I present today with my colleague Jakub Kroll. We are both working at University College London, and we would like to present today our work on how to enable safe handover tasks between different levels of autonomy in highly automated vehicles. First experiments involving autonomous vehicles have begun almost a century ago, though many have predicted that we will have fully autonomous cars on our streets by now. Commercially available vehicles today have maximum level 2 autonomy. So the driver is required to take control occasionally between different levels of autonomy when required to complete an end-to-end journey. These handovers between the car and the driver cause safety concerns, as the driver might not be fully aware of the surrounding situation and the enabled autonomy features instantly, as recent incidents suggest. We have taken inspiration from this video by General Motors from 1956. This was General Motors' vision on how the driver changes between manual control and full autonomy. Imagine that the man in the tower represents the artificial intelligence of the autonomous car. So the transition to the autonomy level is intuitive, human-centered, and safe. So we propose a new interface design for highly automated vehicles, measuring the situational awareness of the driver through physiological and behavioral sensors, giving appropriate feedback through a soft robotic driver seat, acting as a co-pilot, and by that allowing safe, coordinated, and timely transitions between different levels of autonomy. In order to get a sense on how a transition between different levels of autonomy impacts road safety, my colleague will go on from here now. So Jakub.
Hello everyone. I'm Jakub and I work with Jan, and I'll just quickly talk to you about the work we've done on measuring the situational awareness of the driver. So first, in order to get a sense how the transition affects the safety, we analyzed 248 reports on collisions involving autonomous vehicles from 2014 and 2020 that were provided by California Department of Motor Vehicles. And we divided the collisions into two categories. One where it was autonomous vehicles' fault, and the second one it was the fault of other road users, such as conventional vehicles, cyclists, pedestrians, or similar. So we can see that in 16% of the cases, autonomous vehicles were actually at fault. And among those cases, 41% of the crashes occurred during the transition between different levels of autonomy. So one of the most important aspects in the successful transition between autonomy levels is making sure that the driver can attain situational awareness. So what that means is that they can consolidate data around them and into an understanding of the situation, so in order to achieve a safe and timely transition. So in the most universally accepted theory of situational awareness, Ansley defines the situational awareness under 3 levels. Level 1 is perception of critical data through all the senses. And that is in order to identify relevant aspects of the environment. Level 2 is the information processing stage to comprehend the meaning of the collected data. And level 3 is prediction of future states, so that participant can take decision about appropriate action to take. So, in order to obtain an objective measure of the situational awareness, we looked into identifying the correlation between situational awareness and EEG signals. So we collected a new data set using a 32-channel dry EEG headset from 32 participants completing well-established Pebble SAA test, which aims to assess the quality of the situational awareness. Then we constructed a new analytical framework to identify EEG signatures, which can provide an indication whether a person is situationally aware or not. So the framework consists of 3 stages. First, we pre-process data using component analysis. So that will allow us to identify signals which are not associated with a single brain location, but will cover multiple brain areas. Second, we extract features based on spectral analysis. And finally, we classify the samples using random forest. So in the last step, once we have the constructed classifier, we are able to see which combination of spatial structures and frequency ranges is most statistically significant for the situational awareness. So we applied the methodology to collected data, and we identified the most important spatial areas and frequency ranges. And here you can see the results. We can see that there's a relationship between the power spectrum and in beta and gamma frequency ranges and situational awareness. So in general, beta is responsible for attention alertness, and gamma is associated with cognitive functioning and information processing. We can also see that in this photo that there's a strong activation of neurons in the left and right hemisphere. So the right areas, the identified right areas are responsible for vigilance and intuitions, whilst the left ones are responsible for logical and linear thinking. So using the build classifier, we were able to achieve a 67% accuracy on the validation test. I'll give back to Jan now so you can talk about
that. Thank you, Jakob. So to intuitively increase situational awareness, we are creating a soft robotic driver seat. This work includes the creation of a novel hybrid actuation system that allows us to simultaneously switch between pneumatic and hydraulic actuation to independently control position and stiffness of the seat. And I developed the soft robotic actuator with embedded pre-compressed foam and 2 inlets for water and air actuation. The prototype can be actuated simultaneously using a pneumatic and/or hydraulic robotic syringe pump. As you can see here, it is possible to either fully actuate the robot using water or air, a combination of both, or change the ratio of pneumatic and hydraulic actuation. Currently, we integrate this work into our driving seat to prepare experiments in the Land Rover Jaguar driving simulator as soon as the situation let us do that. Future work will explore how to detect situational awareness and the integration of more soft robots into our driving seat and a number of experiments. Thank you very much for your attention. If you are interested in our work, we are happy to get questions from you, either here or via the Slack channel or email or wherever you find us. Thank you very much.